All right. Hi, everyone. Welcome once again to the CUNY Set Theory seminar. And it's a great pleasure, as always, to have my former PhD supervisor, Joel Hamkins, in a way back with us at CUNY. All right, Joel, go right. Let's see. Do I have the topic of your talk? Yes. Joel is going to speak about the surprising strand of reflection in second-order set theory with abundant urelements. That's a mouthful. All right, Joel, take it away.
Okay, great. Well, it's really fantastic to be back here in New York and speaking to all of you and seeing so many friends here and so on. So I want to apologize, as I said, because I'm just going to be going through the draft of the paper instead of having proper slides because I don't have any slides yet prepared. So I hope this is okay. And please interrupt with questions at any time if you have questions, and I'm happy to entertain any kind of questions. So this is joint work with Bokai Yao, who's here, I noticed, and he is a PhD student of mine at the University of Notre Dame. So what I want to do is, let's see, can I do it like this? If I go like this and then make it bigger, is that sort of visible for everyone?
Yep.
This is best. This is best.
Okay. So, and as I said, I put the draft in the chat. So if you joined after a few minutes, maybe someone else can download and then upload that copy again. That's fine. That's just a draft paper. This is current work in progress, but I think it'll be ready pretty soon because it's mostly finished. Right. So I want to talk about set theory with urelements. So this is a kind of traditional way of doing set theory where you start with some already existing primitive objects or atoms or urelements, and you build your set theory on top of those urelement atoms. So the picture maybe is like this. It's a variation of the cumulative hierarchy where the atoms are all given initially at the bottom, and then we form the sets of atoms and sets of atoms and so on. And so, of course, along with that cumulative hierarchy, the pure sets, the ones that don't involve any atoms at all, are also getting constructed, but then the sets outside of the pure sets have some atoms in their hereditary membership. Okay, so the notation, what happened? Oh my gosh, let's see, I'm sorry, somehow I went to the end. How did I do that? Okay, I apologize. Oh, I'm sorry to be so lame about this. Okay, so the notation I want to use is V of A means the whole universe of all sets using the class A of atoms, and I reserve V to refer only to the pure sets, the sets that don't involve any atoms. And then the structure that we're going to talk about is the class of all sets and the membership relation, and then we have this predicate that picks out the atoms. It's true of all and only the atoms. And there's a kind of connection. The atoms are something like the empty set in that they are epsilon minimal. They don't have any members, but they're not sets. So we distinguish the empty set from the atoms because the empty set is a set. In particular, it's a set of atoms. It just doesn't have any elements. So the empty set is not an atom. And this predicate can therefore be defined if you just take the empty set as a parameter. It's the only epsilon minimal object that's a set. Okay, so let's go on then. What? My gosh. Oh, I see. When I'm in this mode, it really wants to go many pages at once. Okay, so what are the axioms of this urelement set theory? Extensionality, you have to change it a little bit because we want to say any two sets with all the same members are identical, but the urelements, of course, don't have any members. And so they all have the same members as each other, but they're not identical. But okay, we just weaken extensionality to be talking only about the sets and not about the atoms. Okay, the other axioms are just the sort of ordinary ones: foundation, pairing, and union, power set, infinity, and separation and collection, and the axiom of choice. And this is all stated in the language with the urelement predicate. One thing to notice is that I'm using collection and separation instead of just replacement. And in CFC, in pure set theory, it doesn't matter whether you use collection and separation or replacement because they're equivalent. But in the urelement context, this is no longer true. You cannot prove collection from replacement. And so we included explicitly on the list of axioms. Okay. So there's some sensitivity to what the exact axioms are because many things that are equivalent in the sort of ordinary ZF or ZFC context turn out not to be equivalent anymore. And so you have to really watch out that you're in the right theory when you're dealing with urelements. Okay, so let's talk about the urelement support of a set. This is just the set of atoms that appear in the hereditary membership hierarchy of that set, or in other words, the set of atoms that appear in the transitive closure of this set. Okay, it's also called the kernel. And so for any class of urelements, we can form the class V of B, which is just the sets that whose support is contained in B. So the pure sets is V of the empty set, because those are the sets that don't have any urelements in their transitive closure. But the entire universe is the union of all the V adjoin W for every set of urelements. Okay, because every set will have a set of urelements that are in its transitive closure, and so this union is constituting everything, even when there are a class of urelements. If you have a subclass of urelements, you can make the subuniverse V bracket B, which is the transitive class containing all pure sets whose, it contains all the pure sets, and also it's easy to see that it's closed under pairing, union, power set, and so on. And so in fact, it will be a ZFCU model if V of A is, okay. So the rank, my gosh, I'm really sorry with this page. When I just do page down, I guess it's because I'm zoomed in and the scrolling doesn't work properly. So I apologize for this completely lame presentation here. Okay, what are we doing? So we did urelement support. Now the rank hierarchy. So in ZFC, of course, we can define the V alpha rank hierarchy. And if you try to do the same thing with urelements, you get a problem, because if there's a proper class of urelements, then these are not sets. And so this is not a set-like iteration. And in fact, it's even worse than just that they're proper classes, but that in general, you can't undertake class recursions like this unless you have the ETR principle. It goes beyond the sort of ordinary recursion principles. And so that way of trying to define rank just is not going to work in the urelement context. But nevertheless, you can still define rank if you just define it by the recursion on sets individually. The rank of a set is the supremum of the ranks plus one of its members, and that is a set-like recursion, set-like well-founded recursion. That defines the rank of any set, even when there are urelements. And then we can define the class V alpha of A is the sets whose rank is less than alpha. But in general, that won't be a set if A is a proper class. Now, one of the main things to observe about, my gosh, this scrolling is really driving me nuts. Okay, I guess I just can't scroll that way. Oh gosh, I apologize. I'm never going to do this again. I should always have the beamer slides. Okay, good God. Oh, it's terrible. Maybe I have to zoom out to prevent this. Okay, so, okay, now, where are we? Okay, so in ZFC, in ZF, transitive sets are rigid, and the whole universe is definably rigid. You can't have two transitive classes being isomorphic unless they're identical, because you can just prove by epsilon induction that the isomorphism is the identity map. That's completely fine in ZF context. But in ZFU, that is breaking down completely, because any equinumerosity of urelements lifts to an isomorphism of the corresponding transitive classes that are built over them. Because you can just define recursively. It's sort of like the Mistowski collapse. I mean, when you define pi of y is the set of pi of x's so that x is in y, it's already defined on the atoms, and then this is extending it to the whole class, and it's going to be an isomorphism of those two universes. And so in particular, when you have at least two atoms, then there will be non-trivial permutations of the atoms. And those permutations all lift to automorphisms, definable automorphisms of the universe. And so that makes a very strong anti-rigidity phenomenon in urelement set theory, which has a lot of consequences that you have to pay attention to. So let's look at some of those consequences. Okay, so one such consequence is this collection issue. For example, suppose we have infinitely many atoms, and let W be the class of finitely supported sets. So these are sets that have only finitely many atoms in their transitive. So so that's a supertransitive class, and it's closed under pairing, union, power set, and so on. And so you can easily see that most of the axioms are going to hold in W. And you get replacement for the following reason. If you have a set in W, so it has finite support, and every element of that set has a witness with a certain property, a unique witness with a certain property, then that witness has to come with the same support, because if it was using some other atom, then there would be many automorphic copies of that witness, and so it would violate uniqueness. And so because of the uniqueness of the witness, the replacement set must come from the same support, and therefore you can the replacing set will also have finite support, and so it will be in W. So it's a kind of lesson that when you have a lot of automorphisms of the universe, then replacement becomes very easy, because it's too hard to have a unique witness, because there's all these automorphic copies of the thing. And so it's a hint that replacement is maybe not really what you want when you're in a highly non-rigid universe. So, but meanwhile, this class W violates collection, because for every n, there is a set of atoms of size n. But you cannot collect those, because the collecting set would have infinitely many atoms in it, but W is the class of finitely supported sets, and so only the finite support sets are allowed. So we don't have collection, but we do have replacement. Okay, so I view this situation is extremely similar to the analogous failures of collection that have been described in other work that I did with Victoria and Tom Johnstone, and also goes back to Zarach, who showed that collection is not following from replacement when you drop power set. So in the theory ZFC minus, a very similar thing happens. And the main lesson, yes?
Just ask a quick question about this phenomenon that you just described. It seems to be crucial there that basically the atoms don't carry any structure, right? Like if you,
Yes.
Are there variations of this where you basically build the universe on top of a collection of atoms that have some structure that are, for example, linearly ordered or something like that?
Yes, exactly right. So if we introduced a well order to the atoms and we insisted that the automorphisms respect that well order, then it would become rigid again and it wouldn't work. That's exactly right. So if we were in a language where the atoms were well ordered, then we would have the set of finitely supported sets wouldn't satisfy replacement anymore, because it would break that argument. So the way I think about it is, okay, the lesson of the ZFC minus case is that ZFC minus, when axiomatized with replacement instead of collection, is the wrong theory, because everything goes wrong in that theory. Even though you have the axiom of choice, you can't prove omega 1 is regular, and there's a whole list of things that go wrong here, ever expanding list. And it's a kind of strange situation, because when you look in the literature, people do axiomatize ZFC minus using replacement. They say, oh yeah, ZFC minus, by ZFC minus I mean, and they list the axioms and they list replacement and not collection. But then they go on and they use consequences of the collection version of it that are not consequences of the replacement version of it. And so it basically, I think, is just a mistake that they made. They didn't have the right theory, because they really wanted the theory in which those other things were following. And so in almost every case that I know of, I think in every case that I know of, the errors that are appearing in the literature because of those axiomatizations are completely corrected if you just change collection, because they achieve collection in the models that they're looking at, and they're using the consequences of the collection version. And so the right axiomatization of ZFC minus is using collection and not replacement. And my view is very similar in the ZFU case. So I want to count collection as one of the fundamental axioms of ZFU. Because if you don't include it, then a lot of things go wrong in a very similar way. Okay, but not everyone agrees with that, and you can definitely find axiomatizations of ZFU in the literature that use replacement and not collection. Okay, so you have to watch out, I guess. So there's other things that go wrong, but let me just press on here. Okay, oh my gosh. When I get to the bottom of the page, it wants the next page. Okay, here we go. So there's another thing that goes wrong, and that is in ZFCU, you cannot prove the omega-1 dependent choice scheme. In other words, there can be a class relation with the following property. Well, let me just give the example, I guess. If you use the countably supported sets instead of the finitely supported sets. So suppose you have uncountably many atoms, and W bar is the class of countably supported sets whose transitive closure has only countably many atoms. Then you can prove collection in that model, because if you have a set with countable support, and everybody in that set has a witness with a certain property, maybe many witnesses, then in fact, you can fix any countably infinitely many more atoms, and you can always find a witness in that new set because they're all automorphic to each other. And so whatever witness is to be found can be moved so that its support is contained in the original set of atoms plus those countably many new ones. And therefore, you can find the collecting set with countable support. Okay, but this model is quite strange because if you think about the class of all urelements is a proper class because there were uncountably many, and so that's not countably supported. But every set of atoms is countable. Okay, and that's a strange combination because you have this proper class, but every subset of it is countable. So in particular, and you have choice. So you can start enumerating. If you try to build an omega-1 sequence, the collection of alpha sequences of ordinals is a proper class tree, and it has no terminal nodes, and it's countably closed because any countable sequence, you can take the union, and that's going to be just a longer countable ordinal sequence of urelements. So it's a countably closed proper class tree with no terminal nodes, but there's no branch. There's no cofinal branch through that tree. So that's a failure of what is called the omega-1 dependent choice scheme. It's different from omega-1 DC on sets because this is a proper class, and because we have choice, we do have the set version of DC. What we're lacking is this class version of dependent choice. Okay, so it's another way in which the urelement set theory is a little bit strange, and that things that you think should follow don't. So you have to be careful. Okay, so let me now explain the connection between urelement set theory and ZFC, how to interpret the one in the other. Okay, so I want to interpret urelement set theory inside ZF. So let's suppose that we have a set theoretic universe of say ZFC, and I have any class A. Maybe A is the class of all ordinals, for example. Okay. And now I'm going to define a certain model that I call V bracket A, or that we call V bracket A. And this is going to be an urelement model in which there will be A many urelements. Okay. And so the first thing we do is we make a copy of A. So every element of A has a copy, which is a pair starting with 0. Okay. These are going to be the atoms of V bracket A. So we put all those into V bracket A. And now we close under the following operation. If I have a subset of V bracket A, then I make this thing, which is a pair whose first element is 1, and that's going to represent that subset as an element in V bracket A. Okay, so I've put in this object into V bracket A, and it's representing the set whose elements are the actual elements of Y. Okay, so I define this membership relation. X as an element is a bar element of Y bar, just in case it's one of the actual elements of the set Y appearing in the second coordinate. Okay. So everything in V bracket A is a pair. If it starts with a 0, it's an atom, and if it starts with a 1, it's a set. And I can tell the membership relation on those guys in the way that I just defined. And it's easy to see. It's set-like and well-founded in V. So I've defined this class structure, the V bracket A structure with the epsilon bar relation. And I claim it's a model of ZFCU with A many urelements. Okay, so first of all, we get extensionality for the sets because two sets are going to have the same epsilon bar members just in case the set that they came from is the same. And so we're going to get extensionality. And foundation holds because epsilon bar is well founded. And oh my gosh, what happened? Let's see. Right. Okay, here we are. So and it's easy to see that you get union pairing power set and so on. It's something like forcing. It's a lot like forcing, because in forcing, when you want to show that those axioms are forced, you take a name for a set and then you build the name for the union set or the power set and so on. You just build the name by hand. And in fact, we can do the same thing here. If I have two elements of V bracket A, then this is the object in V bracket A that will represent the set that has those two objects as elements. Okay, because the epsilon bar elements of this set are precisely U and V and only those. Okay, so now we can see how V is copied into the pure sets of V bracket A, because just let U check be the set whose members are the checks of the elements of U. This is just like enforcing. This is the pure set version of U as copied into V bracket A. And so it's easy to see that the original universe is just isomorphic to the class of pure set of these check names, which are exactly the pure sets of V bracket A. And now we can expand the language a little bit by introducing what we call the urelement enumeration predicate. Okay, a vector. It's not a unary predicate, but a binary predicate, and it associates the copy of little a in V bracket A with the element that is indexed by A. So A bar was the 0, A, and A check was the pure set that's representing A inside V bracket A. And A vector is that enumeration. So it's a function that is mapping the class A, or the copy of the class A inside V bracket A, to the elements. It's enumerating the elements by that class of pure sets. Okay, and now my gosh. Okay, the main thing.
Can I have a question about the construction of V
Sure.
bracket A?
Sure.
So you said that the elements of the V bracket A are the ordered pairs, right? Of 0 and
in
A.
V, they're ordered pairs. In V bracket A, they're
Okay. Yeah. So because I had a question about how they can be or elements if ordered pairs are simply, defined
so
by, I don't know, Kratowski
we're
definition.
building a universe of elements. So we've said, well, we need to distinguish what will become the sets of V bracket A from the elements of V bracket A. And so we just take these ordered pairs. If it starts with a 0, then that's what we're going to say is an element, and it won't have any bar epsilon elements.
So V bracket A doesn't see that they are some ordered pairs. It only sees the elements. Okay, thanks.
Exactly. They have internal structure in V, but that's not visible in V bracket A using the epsilon bar relation.
Thank you.
Okay, so the main observation to make is that the original set theoretic universe is bi-interpretable with this V bracket A structure. And so I defined this structure. It's a certain class structure definable in V. So that's giving me an interpretation. It's a bi-interpretation because V can see how it is copied into the pure sets of V bracket A by the check map that associates every object with its check. So V can see its copy in there, and V bracket A, using the A enumeration, the element enumeration predicate, can see how it arises from its pure sets. It can see the isomorphism. It can see its copy inside the pure sets as implemented by the V bracket A interpretation. So that's a bi-interpretation. And then one can observe a little more, namely, every set in V bracket A is equinumerous with a pure set, because Y bar is going to be bijective with Y check, which is a pure set, because V bracket A can build that isomorphism, can build that bijection. Okay, so I want to just dwell on this issue a little bit. Oh my gosh, I really have a trouble with that. I don't know what it is. Okay, so when good God, what is going on? Okay, so when every set is equinumerous with a pure set, then this is a situation that is philosophically interesting in my opinion, because if every set is equinumerous with a pure set, then every structure, every mathematical structure is isomorphic to a structure in the pure set realm, because you can just carry the structure over to the pure set to which it's bijective. And so that situation is exactly when philosophically you don't need any elements. I mean, from a foundational point of view, if the reason you introduced the elements was to have a better foundation of mathematics, then if you're a structuralist, that situation is exactly when you don't need the elements, because you could have just done it in the pure sets. And I think historically this is has a lot to do with why the standard theory became element free, because people realized, well, we don't need the elements to represent any isomorphism type of a mathematical structure that we want to talk about. And the theory is just much cleaner and better without the elements. And it's foundationally, from a structuralist point of view, just as good. And so that's why we use ZFC today instead of ZFCU, I think. Okay, but one man's modus ponens is another's modus tollens, right? And so the idea is, if you think that elements are important foundationally to represent mathematical objects and structure, then you should probably think that there should be sets, involving the elements that are not equinumerous with any pure set, because that's why you introduce the elements, right? Okay, but now the puzzle is, right, what are these weird primitive mathematical objects that lead to these sets that can't be put into bijection with any pure set? I mean, the traditional candidates for elements were numbers, first of all, and maybe there was resistance to thinking of numbers as sets, and so people wanted to say, well, the natural numbers, I'm going to take them as elements and build the set theory on top of that. Or maybe geometric points was another natural candidate of things that weren't fundamentally sets, and so we treat them as somehow irreducible primitive mathematical objects of some kind, and then take sets of points and so on. But in both of those cases, they are equinumerous with pure sets, because we have the finite ordinals and we have the real numbers as implemented in ZFC and coordinates and so on, and so we can seem to handle both of those kinds of primitive objects without needing the elements. And so, okay, so if you want to do element set theory and you view it as indispensable for the foundations, then I would want to hear more about what are these kinds of elements that lead to these sets that can't be put into bijection with a pure set.
Joel,
yes.
just to bring this up again, it seems again like it would be very natural from that perspective to have elements that do carry a structure, because like what would be the point of adding an amorphous blob of atoms, right? Like you think of things like natural numbers or whatever, things that would be hard from some perspective to reflect by sets. So it seems like it would be the natural thing to do, to have some collection of atoms with some complicated structure where you think this would be hard to replicate by a set or something like that, right?
Right, exactly. But that's what I'm saying. What is this class that you're talking about? I mean, the traditional element candidates aren't like that. Is what I'm trying to.
I understand that, but also just another point. Like you constructed this V double brackets A inside a model of set of C, so it's not all that surprising that in a way that everything.
Right, so we would need some totally different construction to handle that other kind of element situation. Yeah, it wouldn't be interpreted like this. Yeah, exactly.
If I understand correctly, that the interpretation or the by interpretation depends crucially on having this correspondence between the little a check and the little a bar, that you're essentially saying the atoms are enumerated in terms of pure sets a priori, and then from that you get the isomorphism of everything else.
I'm going to address that, because there's a theorem coming up here that exactly is about that point, and that is, okay, so first of all, let me just sort of reiterate, all of these theories are bi-interpretable because of this construction. If you specify a specific number of atoms to have and a specific enumeration, then you're going to get bi-interpretability with ZFC. Okay, that's what the construction provides. And in particular, it follows that ZFCU is not a tight theory. So a tight theory, ZFC is tight, which means that no two extensions of it, if they're bi-interpretable, then they're identical. So that's definitely not true for, oh my gosh, that's definitely not true for ZFCU, because here are by specifying different numbers of elements, we have bi-interpretable theories that are not identical. But if we don't specify exactly how many elements there are, and this gets to Andreas's point, then, for example, in corollary 6 here, no, let's see, what is it? No, I want to go a little further. This one, theorem 7. If I only say ZFCU plus, say, infinitely many atoms, or ZFCU plus a proper class of atoms, then this is not bi-interpretable with ZFC. And so this is exactly addressing Andreas's point, showing that in fact it's necessary, if you want to have a bi-interpretation, you have to provide the enumeration with a specific class, because if you don't, if you just have a theory like this, then it won't be bi-interpretable. And the reason is that the element universe has too many automorphisms, and that's not possible to have a bi-interpretation of such a universe with a universe that's definably rigid like ZFC. So basically the proof says if you had a bi-interpretation like this, then go to a model that had a proper class, then there's going to be automorphisms fixing any desired set and moving things outside of that support of that set. And that is going to prevent you from actually having a bi-interpretation with ZFC, because there won't be any such automorphism of the ZFC model that you get. Okay. So let's press on and talk about reflection a little bit. I realize that everything is taking much longer than I thought because of my problems with scrolling. Yeah, okay. So the reflection theorem, I assume most of you know, the Levy-Montague reflection theorem in ZFC says if you have a formula in set theory, then there's some ordinal lambda so that it's absolute between V lambda and V. And in fact, you can get a proper class club of such lambda for which all the sigma n formulas are absolute in that way. Okay, in the element context, then we shouldn't generally expect to reflect truths from V of A to V lambda of A, because V lambda of A would include every set of atoms. Those have very low rank, but they might be bigger than lambda. If there's a proper class of atoms, then V lambda of A will have sets that are bigger than lambda. And so the fact that every set is bijective with an ordinal won't be true here ever if A is a proper class. So we don't expect to reflect from V of A to V lambda of A. Rather, what we should do is reflect from V of A to some transitive set. So the reflection statement in the element context says that for every set P and every formula, that there's a transitive set V containing that P, so that phi is absolute between that transitive set and V of A. So we're reflecting to a transitive set rather than specifically to a rank initial segment. Okay, if there's just a set of elements, then you can just prove the reflection theorem in the normal way. And even that's true if there are, say, ORed many atoms, you can bleed them in a little bit at a time and get this sort of tower, this continuous tower of the universe, and that's enough to prove the usual proof of the reflection theorem. So what I want to do is discuss reflection theorem just in the general context of ZFCU, where we don't always have this tower, this continuous tower. We can't build such a continuous tower. There might be too many elements. Okay, so first is if every set of elements is well orderable, I'm not assuming AC, I'm just assuming the sets of elements are well orderable, then you can find a set U so that every set of elements that's disjoint from U can be duplicated to another disjoint set of elements disjoint from both of them. And that's not too difficult to see. You just pick a U so that the sets of elements in the complement have as small a cardinality as possible. And then you're always going to be able to duplicate such a set, because if you couldn't, then you could make a better U, is the basic idea. Okay, so this is, you have U for anything disjoint, you can find another one disjoint of the same size. That's duplication. Now, duplication implies homogeneity, namely any two disjoint sets, any two sets of urelements that are disjoint from you and the same size, then there's an automorphism of the entire universe that swaps them. Okay. And that's just because, well, if they were disjoint, then we can make a permutation that swaps them and extend to the universe. And if they overlap, we just find another copy that's disjoint from both of them, and then first go to the other copy and then to the other one. So even if they overlap, it's no problem. Okay, so now using this homogeneity property, we can prove the reflection theorem, the reflection principle, the first order reflection principle. So first we can prove the omega DC scheme. So if you have a class relation and everybody's related to somebody, then we want to find an omega threading of it. And the way you do that is you build a sequence of cardinals. So the first one is big enough so that for some class of atoms, it has some elements in the domain of the relation. And then you look at everybody in that class and you look at the y's that they are related to, and you look at the sizes of the supports of those y's and the ranks of the sets of those y's, and then you get some lambda n+1 that's bigger than all those. And then because of homogeneity, a fixed set of urelements of that size is always going to have a copy of any of the witnesses y. And so we can specify lambda n+1 as a cardinal that's big enough so that you can find y's in a fixed set of urelements of that size, of rank less than lambda n+1. So if you iterate that omega many times and take the supremum, then you can find your transitive set V, which is going to be closed under R witnesses. So every x in V is going to have a y in V, so that x r y. But now using the axiom of choice, we can well order this set V, and then we can find the omega threading by just picking the least one. Okay, so now once we have omega DC, we can prove the reflection theorem in the usual way, because you're just closing under Skolem witnesses, which is the R relation. So what you really want to do is find a transitive set which is closed under the Skolem witnesses for the x's that are in that transitive set. And then that is enough to make phi absolute between V of A and that transitive set V. Okay. So
can I ask a question about the proof of omega DC? So as you're iterating this process, you're building these larger lambdas.
Yes.
And at each stage, you're also enlarging the set of urelements.
No, because they're all automorphic. It doesn't matter which one.
Okay, that's the key. Okay.
Because of homogeneity, they're all automorphic, and so they all have the same ordinals for the ranks and everything, and that's important in the proof.
Thanks.
Okay, so the surprising thing about this proof is that we use the axiom of choice to prove reflection, which is somehow strange because that's not at all how you do it in ZF. In ZF, you can just prove the Levy-Montague reflection theorem with no choice needed, but here we're using the axiom of choice in order to prove reflection. And so does reflection, first order reflection, hold in ZFU? And we don't know the answer to that. But we can prove a number of cases of it. But I want to just skip ahead now, and let's get to the class theories. So just to review quickly, so Gödel-Bernays set theory and Kelly-Moore set theory are two sorted theories. We have the first order part of sets and the second order part of all classes. And the difference between GBC and KM is that in GBC, okay, the sets form a model of ZFC, including allowing class parameters in the collection and separation schemes. But we only have class comprehension for first order definitions. So if phi has only first order quantifiers, then in Gödel-Bernays we're allowed to form this class. But in Kelly-Morse, we allow second order quantifiers in this phi, so second order class comprehension. And both of them also have the global choice principle, which is equivalent to saying either that there's a global choice function or that there's a global well-ordering of the universe, or that there's a global well-ordering of the universe in order type ord. And those are all three equivalent in the pure set context, but that's no longer going to be true in the element context. Okay, so we're going to use in the element context, we're going to use the class well order principle. Every class has a well order, but it's not necessarily order type of word. Okay, so right. So let's also talk about this interpretation of Kelly-Morse set theory in a first order theory. So it's due to Merrick. Also Cameron, who's here, gave a very nice account of this in his dissertation. So we need the class choice principle, which is the principle that says if you have a class and for every element of that class there's a class with a property, then you can find a two-dimensional thing whose sections have the desired property. So if you have KM with the class choice principle, then this is bi-interpretable with ZFC minus with the largest cardinal, which is inaccessible. So that this is what's called the unrolling construction. So the unrolling construction is you take the classes in the original Kelly-Morse model and you think of them as representing a set in this ZFC minus model, which is going to be taller than the ordinals. So so the typical situation, okay, let's see, right. I'm sorry. I first do the easy direction. If we have a model of ZFC minus with the largest cardinal kappa, which is inaccessible, then we can just take the V kappa of that model together with all of its subsets. And that is going to be a model of Kelly-Morse with the class choice principle. So the hard part is the other direction, really. And so, so we have a model of KM plus CC, then we define what's called the unrolling. A membership code is an extensional class directed graph relation with a unique maximal node. So basically, it's something like the transitive closure of a set with the epsilon relation. It's like this, except that it's a proper class object. So we can, for example, make such membership codes that are corresponding to the ordinals or the ordinals plus one or the ordinals squared or much bigger sets that would exist beyond ORD if we had continued the cumulative hierarchy beyond ORD. Okay, so using the classes, we take these membership codes and we want to say that two of them are equivalent if they're isomorphic as directed graphs. And we want to say that one of them is an element of the other one is representing an element of the other one if it's isomorphic to the restriction of the larger one to one of the predecessors of the maximal node. So the maximal node is like the node whose elements are representing the elements of that set and then their elements and so on all the way down. And it's well-founded, that's a proper class, it's well-founded. And so the elements of the set that's coded by E are precisely represented by these Y's, which are predecessors of the maximal node. Okay, and then one can prove, using KM, you can prove that the set W of equivalence classes by these equivalence relations gives you a model of ZFC minus. Okay, and that's quite a nice construction. And part of what I like that Cameron had done in his dissertation is to find exactly what the second order principles we need weaker than KM, going down to GB, and ETR is a big part of that. Okay, I guess some of that also appears in earlier work. So, okay, so let's now do the same thing, but with elements. So we want to have GBCU and KMU. And so now we're going to have the first order part and the membership relation and the element predicate and the collection of classes. Okay, so we're going to have a model of CFCU here, and then the classes for GBCU, we're going to allow first order comprehension, and for KMU, we're going to have second order comprehension. And now, oh gosh, let's see, what is going on here? Let's see. So, okay, oh, we did that already. And now, right. So, oh, it's just, I click on it and it goes ahead. Okay, so, right. Every model of GBC is bi-interpretable with the corresponding model of GBCU using exactly the analogous construction to the bracket construction that I described earlier, for the ZFC case. So you use the ordered pairs again, and you take all the classes are just all the old classes that happen to be subsets of the class of these pairs. And that exactly works. It gives you a bi-interpretation of GBC with GBCU plus a many urelements. And again, it's this Andreas point that we're using explicitly the urelement enumeration predicate here, not just saying that there's a lot of urelements, but specifically tying them to an enumeration with the pure sets. And that gives you a bi-interpretation. And then also it works with KM and KM plus CC. We get it in the urelement context as well. Okay, so that shows you that these theories are all bi-interpretable. We need parameters to give us the class parameters to give us the urelement enumeration. So you can have GBC plus ord many atoms or V many atoms or whatever, and KM plus CC. All of these collections are bi-interpretable. So now I want to come to this axiom, the abundant urelement axiom, which so let's first prove the following. So suppose we have a model of GBCU and kappa is an inaccessible cardinal, then we can cut down to the hereditarily less than kappa sets. Okay, these are the sets of hereditary size less than kappa, but using all the urelements. Okay, so but we only keep as sets the small ones, but the classes will have all of the subclasses of this model. Okay, then the claim is that that this is also a model of KMU. If the original one is modeling KMU, then the hereditary class also models KMU. And that's pretty easy to see because the classes, anything that's second order definable here is going to be second order definable in the original one. And so you're going to have the class existing there. And so it will exist here because we're taking all the classes here that existed there that are subclasses of this new domain. But what I want to focus on is the nature of this hereditary model. So kappa was an inaccessible cardinal, and the ordinals are, of course, are exactly kappa, but the class of urelements is now much bigger because it used to be a proper class in the original model, or ord many even, which is much, much bigger than kappa. So if we had ord many urelements to start with, now we've got this KM model where the number of urelements is extremely big in comparison with the number of ordinals. They're no longer equinumerous. But yet every class is well orderable, so we have global choice in that sense, but not every class can be put into order type ord because it's just much bigger than ord, because the ord of this model is kappa, which is tiny in comparison with the order type of the atoms, which was the ordinals of the original universe V. Okay, so let's observe something about this model. So kappa was inaccessible. We had ord many urelements in the original V, but we cut down to the hereditary sets. Let's say a class is small if it's not equinumerous with all the urelements, but that means it's equinumerous with a set in V. And so in particular, its power set is also small, you know? And so if I have a small class of urelements, then I can, if I is, if B is a small class of urelements, then I can find another small class, which is corresponding to the power class of it, and I can have a set D that lists all possible subsets of B, subclasses of B as the sections, and that will also be small. So in other words, the small classes of urelements have their power classes also small. And similarly, we're going to get a kind of regularity property, namely, if I have a small class, if I have a small class if I is small and I have a class on the product space so that every section is small, then D itself is small because that's corresponding to the fact that ord is definably regular in the original universe. And so it's something like the cardinality of the class of urelements is something like an inaccessible cardinal, is how we're thinking about it. So the abundant atom axiom is the assertion that the class of atoms has those properties. Namely, it's strictly bigger than ord, and every small class of urelements has a small power class, and every small index class of small classes is small. So it's saying that the universe is very wide with respect to atoms in comparison with its height. So now, if you have GBCU with ORed many atoms, then when you do that hereditary cutoff, you get the abundant atom axiom. Now, that's a kind of typical way that the abundant atom axiom might hold. And then we get this by interpretation. If you have Km plus the abundant atom axiom, then when you do the unrolling construction, you're going to get 2 inaccessible cardinals. This kappa comes from the ordinals of the Km model, and the lambda comes from the order type of the urelements of the abundant atom axiom model. So the picture is like this. If you start down here with the KMU plus CC plus abundant atoms axiom, and you do the unrolling, you're going to end up with W, which is going to be a ZFC minus model with 2 inaccessible cardinals, where kappa is the original height of the ordinals, and lambda is the order type of the atoms in the well ordering that was provided, the minimal well ordering. And then, of course, such a model W is bi-interpretable with its element coding by W bracket A. So we can have lambda many atoms here, and also we can cut down to the Km model, which is just chopping off at lambda now instead of kappa, and that's going to be a Km plus CC model in which kappa is still super compact. And this one is bi-interpretable with its element 1. So all 5 of these models, not the V, but all the other ones, are going to be bi-interpretable with each other. That's the basic picture of the bi-interpretation that we're going to use later on. Okay, so now what time is it here? Oh my gosh, okay. So not so much time left. So now I want to move on to second order reflection. So second order reflection is the principle saying in the context of GBC or KM, or also we're going to do it with elements. If you have a second order formula that's true in the second order model of set theory, then there should be some V lambda where it's true at that level, interpreting the second order quantifiers as ranging over the subsets of V lambda. Okay. This is different from second order reflection that appears in some of Vika's work, also with Cy Friedman, where they say second order reflection is reflecting from the whole universe to a coded class of classes in the universe. It's a different principle. We're reflecting to a transitive set, to a V lambda here. And so one has to pay attention. There's different kinds of reflection. So the second order reflection principle has large cardinal strength in the KM context. So for example, if you just reflect GBC itself, which is a finitely axiomatizable statement that's true in a KM model, say, if you reflect that, then you're going to get a V kappa, which thinks GBC is true, but when equipped with all of its subsets, but that means that the second order quantifiers are interpreted correctly. And so it would have to be a model of second order ZFC, which by Zermelo's theorem means that kappa would have to be inaccessible. So we're going to already get lots of inaccessibles coming from second order reflection just by reflecting GBC itself. Okay, but in fact, we get more than that. You can get a stationary proper class of pi1n indescribable cardinals just by pushing a little harder on that idea. And for an upper bound, if kappa is a measurable cardinal, then you can produce V kappa will be a model of Km plus CC plus the second order reflection principle. So let me just explain that a little bit. So if kappa is measurable and phi of x holds in V kappa, so a second order phi, then just apply the measurability embedding with critical point kappa. And so phi of j of x holds in the j kappa rank initial segment of M, yeah, by elementarity. But V kappa and V kappa plus 1 both exist in M. And so, and furthermore, J is elementary from V kappa to Vj kappa of M, which is Mj kappa. And so M can see that phi j kappa reflects down to this structure which exists in M. And so Excuse me. And so therefore M thinks that phi reflected down to an inaccessible cardinal below. And so therefore by elementarity, V must think that phi reflects from V kappa to something smaller. So that shows that reflection holds if kappa is measurable. And you can do better. So omega erdos is enough, which brings it into L. Okay. So here's a kind of curiosity that I noticed. If you have a weak second order set theory, so this is GB without global choice, but just with the set version of the axiom of choice, so every set can be well ordered. Then if you add second order reflection to that, you get full KM plus CC. So second order reflection erases the distinction between Gödel-Bernays and Kelly-Morse. They become equivalent, and you don't even need Gödel-Bernays with global choice, you only need it with set choice. Right. Okay, so now I want to consider this following new large cardinal notion. Kappa is second order reflective if every second order sentence that's true in some structure containing kappa in the domain in a language of size less than kappa is also true in some first order elementary substructure of size less than kappa whose intersection with kappa is an ordinal. Okay, so any big structure has a tiny elementary substructure to which the second order statement reflects. Okay, and we say lambda reflective if it's true when that original M has size lambda. And we can say it's reflective for pi11 or pi1n assertions if we get the reflection for that level of complexity. And now the interesting connection is that this notion interleaves with supercompactness. So every lambda supercompact cardinal is second order lambda reflective. And the reason is that if kappa is lambda supercompact and you have a structure M of size lambda, then you can just take the supercompactness embedding. And the basic fact is that J image M is first of all isomorphic to M and therefore will satisfy phi, but also is an elementary substructure of J of M. And so from the point of view of the image of the supercompactness map, N thinks J of M has this elementary substructure J image M to which phi reflects. And so therefore, if kappa is lambda supercompact, then you're going to get the lambda reflection property. Yeah. And then the super interesting part is that we get the other direction, actually. If we have 2 to the lambda less than kappa reflection, just even for pi11 is enough, then kappa must be lambda supercompact. This theorem is related to the Magador characterization of supercompact. It's sort of a refinement of Magador's characterization of supercompact is how I think about it. So if you have a reflective cardinal at the level of 2 to the lambda less than kappa, then look at H lambda plus. Let me just assume lambda equals lambda less than kappa. So this structure has p kappa lambda in it, and it has all the subsets of p kappa lambda in it, and it has all the functions from p kappa lambda to p kappa lambda, or to lambda. And the question of whether there's a normal fine measure on p kappa lambda is a second order assertion about this structure, because you're saying, can I pick out the measure 1 sets so that it's normal fine, it's normal and fine. But being normal and fine in this structure are first order assertions about the predicate, because you already have all the subsets and all the functions. All you have to do is say the fineness property that for every alpha, the set of sigma that contain alpha is measure 1, but that's just a first order assertion over that structure about what the measure 1 sets are. Okay, and so now, so therefore, if kappa isn't lambda supercompact, then that second order property would reflect. So let's take a first order elementary substructure of size less than kappa whose intersection with kappa is an L is an ordinal. And then this is this tiny thing. We can let S be its intersection with lambda, which is an element of p kappa lambda. And we can use that as a seed to generate a filter. And then we can argue that this filter is a normal fine measure over M as far as M is concerned. And so that would contradict the reflection of the fact that we were reflecting the absence of lambda supercompactness. Okay, so therefore kappa must really have been lambda supercompact in the first place. Okay, so what that shows is that being second order reflective is the same thing as being supercompact, even when you restrict it just to pi11 assertions. So there's this tight connection between supercompactness and second order reflection. Okay, so now, in fact, we get a level by level version. So being lambda reflective for pi11 is equivalent to being nearly lambda supercompact using a notion that was introduced by Jason Schenker in his dissertation about 10 years ago. So nearly supercompact is like a weak compactness version of supercompactness where you have a normal fine filter that measures up to lambda many subsets of p kappa lambda and lambda many functions from p kappa lambda to lambda. And okay. So now let's move to second order reflection with elements. So if you start with a model, so this is really the main observation that appeared in Yao's, my co-author Yao's dissertation and his paper that was just published. What he did was he started with a kappa, which was kappa plus supercompact, and he built a model of KMU with second order reflection and more than ORed many elements. And actually he asked me, because he was using this very strong assumption of kappa plus supercompact cardinal kappa in order to make that happen. And it seemed like it was out of sync with the level of the strength of second order reflection about this indescribability and so on, because the supercompact hypothesis was considerably stronger. And so he asked me, well, do we really need this? And I looked at it and I said, well, it looks like you're really using it in a fundamental way. And so that's what led to this work then, where now we're going to reverse it and show that in fact supercompactness is needed if you push on it a little harder. Okay, so the main observation was that if you have a lambda supercompact cardinal and you make that V bracket lambda, so that's going to have lambda many elements, and then you cut down to the hereditary structure, so this is the H cap of A of that model, then you're going to get second order reflection holding there. Okay, and the proof of that is basically this is a model of size lambda, and because kappa is lambda supercompact, we get reflection for free in that situation because J image H kappa bracket lambda is going to be a model in which is elementary in J of H kappa of A, and so it's exactly the same as the other proof. Okay, so let me show you now. So in fact, the first observation now to make after that is that you don't actually need a lambda supercompact, but being nearly lambda supercompact is good enough if all you want is pi11 reflection. Yeah. Oh, I see. This should say pi11 here, I think. We're not getting full second order. I'm sorry, there's a mistake in the paper here. It should be pi11. Okay. So let's now move to the main theorem finally. So what I claim is that the following theories are bi-interpretable. If you have Gödel-Bernays plus the axiom of choice for sets plus the abundant atom axiom plus second order reflection, actually this theory is identical to the next theory for the reasons that we discussed earlier, KMU plus CC plus abundant atoms plus second order reflection. And the interesting thing is now we're making it bi-interpretable with the pure set theory, KM plus CC plus a supercompact cardinal plus second order reflection. We could drop this CC and so on because second order reflection is implying CC. And so we could put GBC plus supercompact plus second order reflection. And the proof is using the same interpretation that we had before. It's the same picture. So if you have this model with abundant atoms, so that it's very wide in comparison with this height kappa, then if you do the unrolling, you get this model W of ZFC minus where that the kappa becomes inaccessible and lambda, the order type of the elements, becomes also inaccessible. But then the second order reflection principle is going to give us that kappa is super compact in this model up to lambda. And the reason is that structures of size lambda in this model are coming from proper classes here, which reflect to transitive sets, which are of size less than kappa. And so we fulfill the fact that kappa is second order reflective, which is equivalent to supercompact. And so here we have an actual supercompact cardinal. Up here we have that it's supercompact up to lambda and it's lambda reflective. So let me just mention also the pi11 variation. If you drop from second order reflection to pi11, then you also get the corresponding picture where now at the top, instead of having a lambda reflective cardinal, you have a nearly lambda supercompact cardinal, which is this Shanker notion, but the interpretations are the same in this case. So, okay, so I guess that's it. That's all I wanted to say. So thank you very much.
Thanks very much, Joel. That was really, really super interesting. Questions for Joel?
I had a question. So you look at these, the only like structure you put on the urelements is when you have this enumeration of them. But I think as Gunther touched on in a question earlier during your talk, we think of this as coming from ordinary mathematics. And so that would have, you know, if you took like the real numbers, you'd have this certain structure on that. Did you and Bokai look at what happens in the context where you start with kind of ordinary mathematical structures? What
Well, in that case, they would be equinumerous with a pure set because the real numbers
fall into that. Okay.
So and in this situation, when it's equinumerous with a pure set, then you're going to be in this bi-interpretable situation.
But I think, wouldn't this affect some of your results about automorphisms, because your automorphisms have to respect the structure on the urelements? Or maybe that was just only showing up with when you have a proper
automorphisms
class.
are always when you don't have if you're just looking at it as a class of urelements. So if once you fix, say, a well-ordering or something of the urelements, then you don't have the homogeneity anymore because the automorphisms won't respect that. We haven't looked specifically at like having the real numbers as urelements and thinking about homogeneity there. I mean, you wouldn't want just the order, right? You would want
you'd want whatever the full structure is.
the ordered field, but that's rigid, and so you won't have any homogeneity there because once you put the ordered field structure on the urelements, then it's a rigid structure. I mean, the complete ordered field is rigid, and so you can't have any automorphisms, right, of it. So it would ruin the homogeneity, and so I don't know if that answers your question or not. So all the homogeneity arguments are in the case when you don't have that structure.
Yeah, I mean, I think it does. I guess it sounds like there's not much interesting set theoretics going on when you add this extra structure.
Let me make a comment about one word in Cameron's question. I think he mentioned you have only this enumeration. What if you had something like the structure of the real numbers? My inclination is to view it the other way around. That enumeration is an awful lot of structure, much more than you would get from the real numbers, because you can interpret the real numbers in pure sets, and now you've got these atoms labeled by pure sets. So that enumeration of the atoms is a very powerful structure. Well, as some of the results show, it propagates upward, gets your isomorphic copies of everything, and so on. And it includes things like the real ordered field and practically any other structure that mathematicians would normally look at.
Right. Yeah, I think that's right. So, but I mean, just to emphasize, the main theorem doesn't have that enumeration in it, right? So we're in the situation in KMU plus abundant atoms. The atoms are not even bijective with any pure class, right? So it's impossible. I mean, that's exactly what the abundant atom axiom, it says there's more than ord many atoms, and so therefore you can't have any such bijection when you have the abundant atom axiom. So that the interesting situation is, I mean, in a sense, there's another way of thinking about the abundant atom axiom. Why would you ever want to entertain the idea that the set theoretic universe was like that with so many atoms that it was wider than it is tall? Because the fact that there were abundantly many atoms is just proof that you didn't finish building the set, you didn't finish building the ordinals. You should have gone taller. And the by interpretations with the unrolling construction are exactly telling you how you might have continued, and you probably should have. And so once you have if you have global choice in the sense that every class can be well ordered, including the class of all elements, not that we're fixing such a enumeration, but just that there is such a class, then if that's not in bijection with the ordinals, then you're in a situation where you probably should have built the ordinals taller, right? And so why didn't you do that? And the fact that if you are in this extreme case of the abundant atom axiom, then because it's bi-interpretable with Km plus ord many atoms, then there's a sense in which maybe you should have built the universe tall enough to cover the atoms, and then you would have just ord many. And so, and then we would be in the situation when we do have an ord enumeration of the atoms.
So would maybe a motivation to have more atoms than there are sets, so to speak, be something like maybe you just want to build a model that has, for example, maybe a measurable cardinal or something like that, but you just throw in kappa many atoms and a predicate for the ultrafilter, and then you build just a few steps until you reach a model where you have, I'm just thinking about ideas for how you could make a model where the atoms have a structure, like maybe they carry some normal ultrafilter, and you reach a model where you can talk about this without going all the way up to a measurable cardinal or something like that.
Oh, I see. That would be interesting. Maybe Yao, if he's still here, can remark on what is the reason to look at the theory of KMU with more than ord many elements? What, because you were studying that before you ever met me, I think. And so what was the motivation?
Yeah, the original motivation was to see if second order reflection implies this principle of limitation of size, because we can easily show that second order reflection implies all these second order choice principles, including the well ordering principle. So I got this question, well, because in the urelements set theory context, these second order choice principles, they come apart. So I got this question whether second order reflection can also give us this strongest second order choice principle, namely limitation of size. Then I figured out, well, assuming we have large cardinals, the answer is no. And of course, to get a model of that, we need more than or many atoms. So that was the original motivation.
I see. Okay, so in a sense, that's you wanted to look at it because you wanted to prove that it originally maybe that it didn't happen, but then in fact it did, and you proved it by this nice large cardinal construction. I mean, because of course, if I'm understanding you correctly, you're saying that maybe one would have hoped originally that perhaps second order reflection would imply limitation of size, in which case the elements would have to be in bijection with ord. But the fact that it doesn't is what you proved by producing the model which required the large cardinal strength. But still, I think maybe ultimately one can still look at the theory as a bit strange from a foundation of math point of view, because when you have so many atoms, then you should have built the cumulative universe taller, right? I mean, especially if it's well orderable. It seems like you're committing yourself to these bigger ordinals, so why don't you have them as actual ordinals instead of only as the coded versions of the ordinals with the classes of elements?
That sounds very similar to what I guess is the original motivation for axioms like replacement or collection. Zermelo set theory has this natural model V sub omega plus omega, but it's got all these well-ordered things in it that are way taller than the universe. And as you said, therefore you should keep going.
Right. Yeah, I think that's right. Yeah, that's a good point. I mean, of course, no model of set theory is ever going to be closed under that completely, because once you have ORed, whatever it is, then you can define a well ordering of type ORed plus 1 or ORed plus ORed or ORed squared and so on. And so you can't ever be closed under
This is a well-known principle. Yeah, once you have ORed, therefore you don't have ORed, says Morale 40.
Exactly, right. So, but I guess there's the idea that
I'm a set theorist, not a class theorist, so there's a difference there.
I mean, the principle, I guess, that you were just referring to, though, is something like every small well-ordered class should be instantiated with a set. And that would imply the negation of the abundant element axiom, right? So if you had some class of atoms that was well orderable and wasn't bijective with the whole class of atoms, then you should have it as a set. So you couldn't ever have more than ORed many elements in that case.
I had a question, Joel. I had a
Sure.
question about if you started with, I don't know, 7 elements in the universe or maybe more, and then you forced to another universe, does it change the?
I see. So I understand how to. So if we have only 7, then we can interpret that with the pure sets, and we can force over the pure set model like normal forcing, and then reinterpret again afterwards. Or if you have a set number of elements, that would always work. But in general, forcing over ZFU, I haven't quite thought about it enough yet. And actually, Yao is working on this now, I think. Forcing over set theory with elements, I think it's an interesting topic. I think in the case when the model is bi-interpretable with its pure sets, then basically there's nothing to say, because it's just going to amount to forcing over the pure sets, which we already understand quite well, and then reinterpreting in the extension. And so really one wants maybe to look at forcing over models of element set theory with way more than 7 elements. You want some weird set of elements that isn't bijective with any pure set. So in particular, not well orderable in order type less than ORed. And in that case, I don't understand how forcing works very well yet.
And I just want to make sure, like when you said, like if you had a universe with 2 elements and one with 7, are those? Did you say that those are isomorphic or
not isomorphic, but they're bi-interpretable?
Okay.
So, because they're both bi-interpretable with the pure sets. Because when you have the pure sets, you can pretend that you added these elements, as many as you want, any set number of them. That's what the V bracket A construction gives you. So if you had a set number, you can do it. You can undo that and go back to the pure sets, and then add any other number that you want. And all of those are, in a sense, the same. They're not isomorphic models. They don't have the same theory, because they think there's different numbers of elements. But in a sense, they're equivalent theories, semantically equivalent, because they're bi-interpretable, which is, one of the tightest ways of saying that 2 models are fundamentally the same, is to say that they're bi-interpretable.
Okay, thank you.
Yeah. About forcing over models with lots of elements, I wouldn't be at all surprised if this is in the work of Vopenka and his school. For instance, Vopenka Hayek book on semisets. The problem is digging it out of there. And it's been a long time since I looked at that book.
Yeah.
I confess, I wrote a review of it, but that was in prehistoric times.
I've heard that every single idea in set theory, including those that haven't been published elsewhere, is already included in that book.
That's very nearly true, but it's well hidden.
So Joel,
Maybe the letters in the book a little bit to get new ideas. Just kidding, sorry.
So
Okay, go ahead, sorry.
Yes. I really like this version of second order reflection that you have. And my question is, are there any interesting questions about the structure of KM with this principle that you know about?
With
Like,
second order reflection, or
yeah, is everything understood, or is there something there to work on? Because it's very
well,
nice.
the equiconsistency isn't exact. There's these bounds, I guess. So maybe one would want to say something more precise about it. I mean, there's omega Erdos and there's indescribables coming below, and my understanding of it is that we don't have an exact large cardinal equivalence there. So that's one thing, I guess. Yeah, I'm not sure. Maybe Yao knows something else.
With KM and second order reflection, yeah, that's also all I know, I guess. Yeah, but with KMU plus second order reflection, yeah, I guess the question of the exact strengths of KMU plus RP2 plus more than or many atoms is still open. Because we know that it's bi-interpretable with CFC minus plus a kappa plus nearly super compact, but we don't know the strength of that theory yet.
Yes.
Yeah.
So there's in Jason's dissertation, he proved that if kappa is kappa plus nearly supercompact, then AD L of R holds. So it's definitely strong if you're in a ZFC context. But the bi-interpretation that we're getting with KMU plus second order reflection is with a ZFC minus plus the largest cardinal kappa is nearly kappa plus supercompact. And I don't know how strong that is. And I was talking with Gunther about it. I was hoping that Gunther would just tell me, oh yeah, it still implies ADL of R, but evidently that's maybe not quite as easy, but maybe there's still hope to get strength out of that. I mean, it seems very likely that it should be strong. Maybe we can just prove at least it's implying the consistency of a measurable or something.
Any more questions? All right, Joel, thanks very much again. Great talk and a great discussion afterwards, and good to have you back at least for a little.
Thank you very much. And I apologize again for my completely lame slide presentation. And I think I'm never going to do that again. So.
I mean, slides are better. Sorry, Joel.
I think so. I had to do my taxes.
I thought it was kind of nice. It was kind of like sitting down at a table and going over the preprints. Okay, even though the flipping head would not have happened. Okay.
Sitting at a table with a preprint and a strong wind, maybe?
I'm sorry, what?
Sitting down at a table with a preprint and a strong wind, just blowing the pages everywhere?
That's a good analogy.
Yeah, that's what happened. It's kind of gusty in here. Yeah.
Nice break, everybody.
Okay, bye.